Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is isentropic nozzle flow, and the section in the textbook is 17.3. Here are the two learning outcomes. At the end of this, you will understand what a converging diverging nozzle is, and you'll be able to determine the properties throughout the length of a converging diverging nozzle. So let's first kind of go back to this example that we did at the end of the last video. And what we did is we had this set of inlet conditions, a pressure, a temperature, an inlet velocity, and a mass flow rate. And I said at the outlet of the nozzle, it was 1,000 kPa. So we had a 500 kPa pressure drop through this nozzle. And we found those outlet conditions at this point. And so I'm going to return to this problem. I'm going to go ahead and look at it in EES. And it's going to go ahead and permit us to go ahead and do some variations in this parameter, the outlet pressure, and see what the results are in terms of the geometry of this nozzle. So let's go over to EES. Okay, and I've set up previous problem in EES, and so I'll just remind you what we had in there. We had our inlet pressure, which was 1,500 kilopascals, and because it came in at such a low velocity, with 1 meter per second, which is relatively small, the stagnation pressures and temperatures were essentially the inlet temperature and pressure. And so then I have it as 1,500 kPa, and I've converted the temperature to absolute 473. We use the ideal gas law a lot in doing compressible flow equations because we're usually using air, which acts as an ideal gas. It's nice to have that in terms of absolute temperature. There's my mass flow rate of 1 kilogram per second. And the next three lines are just some air properties. K is the ratio of the heat capacities, and we're going to assume it's constant about 1.4. There's our heat capacity C sub P. And notice I've converted it to joules per kilogram Kelvin, and you'll see why I've done that a little bit later. But so it's 1,005, and the value of R is 0.287. I've left that in kilojoules per kilogram. You need to be a little careful with your units because we're dealing with velocity terms and enthalpy terms that are often expressed in meters squared per second squared or kilojoules per kilogram. All right, the next line there is we say that this is an isentropic nozzle. So all the expansion and compression has happened isentropically. And so you may recognize this equation. This is T2 over T1 is P2 over P1 to the K minus 1 over K. This is at chapter 7, assuming a constant heat capacity for an isentropic compression or expansion, either one. The next one is the energy balance, where I'm balancing enthalpy and kinetic energy. And so I'm totaling up the total amount of energy, that's Cp times T naught, which is the stagnation temperature. So this whole term on the left would be the stagnation enthalpy. And then I've got my enthalpy term and then my kinetic energy term to add those together. As we said, it's an ideal gas, so the density, I'm calling that rho, is P over RT. And there's my mass balance. The mass balance is the density times the area, and then V here is velocity. Right? So the area times the velocity times density is going to be the mass flow rate. And then I'm defining the pressure drop, which is going to be the outlet pressure. And the way I do it, and this is because we want to do some variation, I'm saying dP is P naught, the inlet pressure, minus P. So P is going to be the outlet pressure that we're finding, and then I'm saying the pressure drop is 500. So then we're going to go from 1,500 to 1,000. And then the last thing is just some definitions in terms of what the speed of sound is. The speed of sound is the square root of K, KRT. And actually I'm missing an R in there, it looks like. Yeah, I was missing an R. I've added it now. So we've got the square root of KRT. And then I've put in this factor of 1,000 because my units on R were 0.287. And this right over here, to get my units in terms of a velocity, meters per second, I need to multiply R by 1,000. So that's why I've got the factor of 1,000 in there. And the definition of the Mach number is just the velocity over the speed of sound. All right, so let's go ahead and solve this. And what we should see is the answers we had in the last video, in which we see here's our outlet velocity at 322 meters per second. We have our outlet temperature of 421. Temperature has gone down. That's always a good sanity check. If things are going faster, we expect the temperature to go down. And we're at about Mach 0.78. Okay. So that's just the problem that we did before. But what I want to do now is I want to look at and vary some properties. And what I'm going to go ahead and do is vary dP, or the pressure drop. So I'm going to go ahead and just remove that and create a parametric table. And so what we'll do is we'll look at variations in the pressure drop through there. And so let's go ahead and look at what the area of the nozzle is as a function of that. And we will also look at what the velocity is. And we can also look at the Mach number. Okay, so I'm going to go ahead and put in some properties here. I'll start off with a pressure drop of 50. And we'll go ahead and just increment that every 50, so we're just kind of making longer and longer nozzles each time. And all right, so we look at our properties. What we see is the area is decreasing. Actually, those numbers are small. I'm going to go ahead and change the area to go ahead and make those numbers a little bit smaller, or larger so you can see it. So we'll go ahead and divide A by 1,000 over here. Okay. If I do that now, I can realize that my area, actually let's do 10,000 because then it'll be in square centimeters. Okay, so I just changed the area. So now the area is in square centimeters. It's a little easier to see than all those zeros there. And so I realized that as my pressure drop gets larger and larger, I'm getting a smaller and smaller area at the outlet of the nozzle, which wouldn't be surprising, and the velocity increases. And so we can go ahead and create a plot of that just to look at it. So let's go ahead and look at what our cross-sectional area is. And as we see, it goes ahead and decreases, which is sort of what we would expect. Okay, what I'm going to do, though, is let's go ahead and add some additional runs to this and look at even larger ranges of the pressure drop. Go ahead and add another 10 runs to this. So we can look at even larger pressure drops. Now it's going to go from 50 to a pressure drop of 1,000. Now if we go ahead and run this, what we look at, if we look at our area and look at the numbers, we're getting down to about 3.5, but then they start to go up again, 3.9. And let's go ahead and look at the plot of that. So again, we'll look at the cross-sectional area. And what we see here is that the area starts to get large at the end. So it's a converging and then it's a diverging nozzle. We realize there's a neck, or the throat is occurring down here at about a dP of about 700, so a pressure drop of about 700. Now, we go back and look at our results table, realize our velocity continues to increase as we go down. So the outlet velocity is the largest, 500. So the velocity continues to increase. The other thing, if you look, the Mach number is occurring right there at the minimum of the area. The Mach number of 1 is right there at the minimum of the throat. So not just kind of as we expected, the fastest velocity occurs at the throat, which is the minimum area, which is a Mach number of 1. Okay, so what we just saw is that there's a particular nozzle shape. It's a converging, diverging nozzle if we have a supersonic outlet. And I kind of want to just return a little bit about why that shape is more or less determined exactly what we have. So let's look at a very small nozzle here. I've got inlet conditions of 50 C and 200 kPa. And let's go ahead and make this a really short nozzle. So it only goes down to where the next pressure, let's say, is 199 kPa. So it's a really short nozzle, very small pressure drop. And now that I've specified this, the other thing I'll do is I'll say it is isentropic. So the flow through here is isentropic. And if I say it's isentropic, that means I've now determined what the temperature is at this point. Because we can use this relation, T2 over T1 is P2 over P1, K minus 1 over K. Here's my 1 conditions. From that I can go ahead and find point 2. And just for giggles, let's say that the temperature down here is now 48 degrees Celsius. So I've determined what that temperature is. Now if I know the pressure and the temperature, I can go ahead and find the volume, because we know if it's an ideal gas, PV over RT. So there's my volume, or more or less I have my density. And if I knew what the mass flow rate is through here, I could then go ahead and determine what the cross-sectional area is, because we know what the velocity is, because what we have, and what's going on in the nozzle, we're just changing enthalpy with kinetic energy, and the enthalpy, well, that's Cp times T. We know how much the enthalpy went down, so that's going to be our increase in kinetic energy. So we know what the velocity is going to be at that point, which means we know what that cross-sectional area is. So the size of the nozzle at a pressure drop of 199 is determined. And we could keep doing that and determine what the next outlet would be, and the next outlet would be, and we're going to go down to 198 and 197 kPa. We keep going, and what we just saw with that EES example is that at one point we start to get to the where it's going to diverge as well. But every time the area is determined as soon as I said it was isentropic. As soon as I said it's isentropic, the shape of that nozzle is determined. So there's only one nozzle shape that is isentropic, and that's the one that's required in order to give you supersonic flow. In fact, what we'll see is as soon as you change that nozzle shape, what you're going to end up doing is forming a shock wave at some point, and so you're going to end up losing your supersonic flow. Okay. I want to talk a little bit about things that are called the critical properties of the throat properties. So first, let's just go ahead and return to this stagnation temperature. Remember, stagnation temperature is just sort of a measure of the total energy in the flow, because I'm adding an enthalpy term and a kinetic energy term, and those two are what happens in a nozzle is energy goes back and forth between enthalpy and kinetic energy. So this is more or less a measure of the total energy. And then just I could go ahead and take a couple definitions, and these aren't energy balances or anything. These are just some definitions. And so this one over here on the left, this is just an algebraic rearrangement from the definition of K, which is the ratio of the heat capacities, and R for ideal gases is Cp minus Cv. So it's just some relations there. And then the second one over here is just the definition of the Mach number. And then over here we have is the speed of sound. We were able to determine that using energy and mass balances. And then in the fact that it's an ideal gas. So just some definitions there. I can go ahead and use those, a bunch of algebra, stick it into that equation for the stagnation temperature, and you get this equation here. So let's just look at what this is. This says T over T naught is, and I've just got some constants. I got K and some numbers 1, and the Mach number. And so that means given a stagnation temperature, the temperature at any point is just a function of the Mach number at that point. Right? So just a function of the velocity, right, effectively. So I can go ahead and figure out the velocities. I need to know what the total energy is going in, and then at any point I know what the velocity is, I know what the temperature is. And that's what this equation gives me right here. I can then go ahead and get another equation for the pressure. And if you look closely what this is, this term right here is just the same term. I got this exponent. All that is P2 over P1 is P2 over P1 to the K minus 1 over K. So that's all that equation is right there. So once I know the temperature and the pressure, so then we can say the pressure is also a function of the Mach number. And not surprising, I can also do the density, and this comes from P2 over T1 is V1 over V2 to the K minus 1, and then V being 1 over rho. Anyway, compressible flow tends to use density instead of specific volume, but that's where this equation comes from. So now I know that the density is a function of the Mach number. So all the fluid properties are all just a function of the velocity, a function of one parameter. Now we also saw in that EES example that at the throat the Mach number is 1, and so if I wanted to know what the properties are right at the throat, all I need to do is set this term right over here to 1, and I can go ahead and solve for what the temperature is. In the book you'll see it uses values like T star and P star, and they list the equations, and it's pretty straightforward. Just put 1 into this equation right here, and you get those equations that they're showing in the book with the stars. All right, so there's a couple ways you can get those properties, and so if you look at, this is table A32. Okay, so first let's go and look at A32. It's in the left-hand column, the independent variable is the Mach number. Remember I saw on those previous page there, we just had all the properties, temperature, pressure, density, etc., are all just functions of the Mach number. So once I know the Mach number, I can determine what that is. So if we look over, and just go ahead and ignore this first column, it really isn't ever used all that much. Don't worry about MA star. If we look over at the middle column, there we have P over P naught, and I figure out what my pressure is, and it just shows that the pressure drops as the fluid gets larger. Here, the last column is the temperature. I can go ahead and determine what the temperature is throughout. And all those tables those are just tentative values of these equations. These equations are also in the table A32, and these are the ones I just showed you on the previous page. And again, don't worry about that MA star when it's really not used all that much in what we are doing. The other thing we can do is if I look at the area equation here, this is the area over the throat area. So remember the star is the throat, so now I can figure out what the area is at the throat. And if I go and look right at Mach 1, not surprising, the area of the throat area is the same as the area of the throat. And then I realize the area gets larger. So this is what we saw in that EES example. Area decreases, area increases as well. So you can either use the table or you can plug it into the equation. Using an equation solver, it's a lot easier to use equations. If you've got nice round numbers, you know the Mach number, for example, 1.8, you can just read those values right off this table. There's also this graph, also in table A32. It's not quite as easy to get accurate numbers because you're reading off a chart, but it's nice to kind of qualitatively see what's going on. So for example, here I look at the area that we saw of our nozzle, converging, diverging, so we know what it looks like. We realize that, yeah, okay, our temperature is going to decrease as we go through the nozzle. Not surprising, our Mach number is going to go ahead and increase as I move through. And so the graph there is kind of better just for qualitative ideas of what's happening. I usually use either the table or the equations to go and determine what the properties are in the nozzle. One way to think of this is that I kind of put this is a picture of a converging, diverging nozzle. They're actually looking at shock waves here in the bottom, but you can just see here's the shape of the converging, diverging nozzle. And so the throat is right there at Mach 1. And so you can kind of think of this table. I've kind of aligned it this way in the fact that Mach 1 occurs right there. If I want to know the conditions at the inlet, it would be right there on that line of the table, that line of the table. I'm having the flow go from the top to the bottom. And then here I'm in the supersonic region. Maybe that's Mach 2.4, Mach 2.8, Mach 3, etc. So more or less this table is sort of like a nozzle that is oriented vertically. So you can kind of think these are all the properties throughout the nozzle in that table. Okay, let's do an example. And the problem says I've got air entering a converging, diverging nozzle. I've got an inlet temperature and pressure. I'm told it's a relatively low velocity coming in. And the back pressure is 20 kPa. Back pressure is the outlet. So, for example, if this is my converging, diverging nozzle, it tells me that the pressure at the outlet right there is 20 kPa. So that's what the wording of back pressure means. And it asks what the exit temperatures and velocities are. Right. So what we want to do is we first want to determine our stagnation temperature. Always the first thing we want to do because everything's going to be a ratio of that. So T0, well, T0 is T1 plus the velocity squared over 2Cp. And when they said the inlet velocity is more or less 0, so you can neglect that term. So it's effectively just equal to T1, and T1 is 20 degrees Celsius or 293 Kelvin. So there's my stagnation temperature. We can also find our stagnation pressure, and because that low velocity, the stagnation pressure is essentially P1, which is equal to 100 kilopascals. Right? So we've got our stagnation temperature and pressure. Those are just measures of our inlet conditions and kind of the measure of the total energy that I have. And the other thing I'm told now is that the outlet is 20. So that's the thing that I know. And so 20 kPa is the pressure at this point that I'm trying to determine properties. If I go back to this previous table, if I look, I've got, let's look at this middle column near the middle, P over P naught. Right? I know what P naught is, and we just found out that it's 20 over 100, so it's 0.2. And so I can go ahead and just find my properties at this line right over there. Oh, sorry, not Mach number 0.2. This value here is 0.2. And so my value is going to be somewhere in the table right here, somewhere between these two values that I have, 0.23 and 0.17. Right? So that's what I know. I know that P2, calling P2 the exit, over P naught, which is 20 over 100, or 0.2. And so it didn't have a nice number on the table, and so I'm going to go ahead and use the equation. And so kind of going back here again, I'm going to use this equation right there for the pressure. I know that's 0.2, and that is 1 plus K minus 1 over 2 Mach number squared minus K over K minus 1. So I'm going to solve this equation for the Mach number. Take some algebra, just use the equation solver on your calculator, and you find out the Mach number is 1.71. And in fact, if we kind of go back, we can do the sanity check, and yeah, so we saw it was between these two values here, which was somewhere that would be the right Mach number. So we know our outlet Mach number, and everything's just a function of the Mach number at that outlet. So now I can come back and bounce back again. I can go ahead and find out what the temperature is. Okay. Find out what the temperature is. T over T naught is a function of the Mach number, so I'm just going to plug that in there to find what T2 is, or T at the exit. I find out that's 185 Kelvin, and it went down from 293, sanity check. Going faster, I expect the velocity to go down. And the last thing we're going to do is find the velocity. And so we know the Mach number, and the Mach number, well, that's the velocity normalized by speed of sound. So we need the speed of sound, that's the square root of K times R times T. So we'll go ahead and put the square root of 1.4. My value of R of 287. to make sure my units work out right, and then I'm going to put in my 185 in there for the temperature. So I know the speed of sound at this outlet is 272.6 meters per second. I'm going 1.7 times that fast, and so my velocity is going to be c times the Mach number, and that velocity is going to be 466 meters per second. So I was able to find the conditions at the outlet. In fact, I could find the conditions at any point. Just kind of read down that table and either use the table or the equations.